Hey guys, Mr. Krieger, AP Exam Review 5, Basic Hypothesis Testing, and by basic I mean we're not going to include the two sample tests. So let's go take a look at the first problem. Okay, more than 200,000 people worldwide take the GMAT, the GMAT exam, each year as they apply for MBA programs. Their scores vary normally with a mean of 525 and a standard deviation of 100. 100 students are randomly chosen to go through a rigorous training program designed to raise their GMAT scores. If the student's average score is 543.1, perform a significance test to determine whether the training program improves students' GMAT scores. Okay, so the task is to state the population and parameter of interest, state the null and alternative hypothesis, state the type of test used and the conditions for the test, calculate the test statistic and the p-value, and write your conclusion based on a significance, an alpha level of 5%. Now, before you do anything else, this is really what you should be doing on every single hypothesis test. You should always be doing every one of these things that are in this list here. The first thing you might want to do is you might want to identify what kind of test you're using. That'll be helpful. So we know that generally speaking that the GMAT scores are 525, but we took a sample of students who went through this rigorous training program and their sample performance was 543.1. So we just want to see if they improved over the normal the standard test score. Okay, they gave us sigma, the population standard deviation, which means that we're going to be using a z-test. As I've told you before, this is a rarity. Normally in the real world, you're not given the population standard deviation, because if you knew the population standard deviation, you would know the mean that you were looking for. So it's not very realistic. But being that they gave that to us, we're going to be using a z-test. And normally, since they wouldn't be giving that to us, we'd be using a t-test, okay? So, state the population that we're dealing with. The population is students who take GMATs after rigorous training course. Okay, and the parameter that we're measuring is the result, the average result on the GMAT. Okay, the average. So we're trying to find the mu value for this particular group of people who have taken this rigorous training course. Now, we want to state the null and alternative hypotheses. The null hypotheses, remember what I always tell you, we're always assuming that there's nothing going on, there's no change, so we're going to say even after this rigorous training course, there's not going to be any change from what students normally get on the GMAT, which is 525. You always use mu here. You never put X bar here. We're measuring to determine what the true population parameter is, not what the sample parameter, what the sample is. We know what the sample is. We're trying to estimate the parameter, so it's mu. The alternative, though, is that we want to show that this program actually works, and that if you take the rigorous training program, you're actually improving your GMAT grade. Okay? Okay, the next thing that you want to do is you want to check the conditions. And remember, for our purposes, there's always going to be three conditions that you're going to check. One condition, the first condition, is going to be, SRS. And you're going to have to check to see if it says it in the problem. And I'm sure it says it in the problem someplace. 100 students are randomly chosen, so SRS as stated in problem. And then we're going to do the normality condition. There's a bunch of ways of checking this. In our particular case, how many students took this took the size of our sample? 100 students are randomly chosen. So because we have a relatively large sample, we could say by the central limit theorem, well, I'm just forgetting my train of thought here. The sampling distribution is approximately normal. Nothing is ever truly normal, but this would be approximately normal. And then in terms of independence, and this is the third and last thing you have to check, you have to make sure that the training program has at least 10 times the number of people in the sample. And there was 100 people in the sample, so 10 times 100. You need to have 1,000 students in training program, and you should say that sounds like it's a reasonable thing to meet. It's reasonable that there are 1,000 people in the training program, and you chose a sample of 100, or at least 1,000 people. Okay, so now this is really, really important. You want to state what kind of test you're using. And because we're given the population standard deviation, we're going to be using a z-test. And it happens to be one-sided because we want to make sure that we want to see if this improved the score. So it's one-sided because it's greater than. All right. So now we go to our calculator, and we're going to put these key pieces of information in. You go to stat tests. And remember, your intervals, your confidence intervals, and your hypothesis tests are in there. The hypothesis test is going to be your basic z-test. We have data. The mu value that we're given is 525. The population standard deviation is 100. Oh, I'm sorry, wrong thing. We have not data but stats. So 525, 100. The x bar that we have is 543.1. And there was 100 people in the sample, and we want to make sure that we want to see if the training program actually increased. So we want to see if it's greater than our null hypothesis, greater than mu, and we should really draw to see what this looks like. Okay, so there you could see the shaded region. You should write down your z-score. Your z-score is 1.81 with a p-value of 0.0351. Okay, so now we got to figure out what this means. So since the p-value is less than 5%, and that's what they were telling us to look for, what would you say about the null? Do you say we should reject the null or fail to reject the null? Well, with such a small p-value, relatively small p-value, we'll reject the null in favor of the alternative. So you could say with z a value of 1.81 and p equal to 0.0351, we reject the null hypothesis. No context here, but we need context. So you could now say, here's where you put your context in. We have evidence. You never say we proved anything. We have evidence to suggest that the training program increased GMAT scores. Okay? So that's how you do a hypothesis test. Okay? All right, let's take a look at another one. It's going to be similar. There'll be some small differences, and we want to take a look at those differences. Okay. You're doing a study on vaping and want to determine if the percent of those who vape at Hewlett High School is different from those of high schools across the nation. So we're comparing basically Hewlett High School to national numbers. The national percent of students who vape is 23%. By the way, these aren't real numbers. I just made up an example so you can appreciate it. You take a random sample of 86 Hewlett High School students and find 13 of them vape. Okay, again, it's a random sample. That's important. Is there evidence that there's a difference? So here we're not asking if Hewlett has a larger percentage or a lower percentage of students who vape. We just want to see if it's different from the national average. So what do you think that's going to be? That's going to be a two-sided test, because we just want to see if there's a difference, right? So that's a two-sided test, two-tailed test. And what do you think you're going to use here? Well, this is a percentage stuff. This is proportions. So proportions are always a z-test, and you're going to use a one proportion z-test. That's what you're going to use when we get to that point, okay? So we're going to state our population. Our population is Hewlett High School students, all Hewlett High School students. What are we measuring? We're measuring the proportion of Hewlett High School students who vape, okay? And now we're going to state our null and alternative. Our null is that, Hewlett High School is just like the rest of the country. We're going to put, you don't put a p hat here. P hat is the statistic. P is the value of the parameter value. So that's going to be 0.23. That Hewlett is just like the rest of the nation, 23% of them vape. Then the alternative, because it's a two-tailed test, we don't know if Hewlett has a greater vaping group or a lesser vaping group, so we're just going to say the proportion doesn't equal 0.23. Okay, and now we're going to check the conditions. The conditions for proportions are not like the conditions for means. You've got to check, two of the three conditions are the same, the SRS and the independence. What's different is the normality. Normality is always checked by doing n times p. All right, so SRS, so these are our conditions, SRS, so we'll just say stated in the problem. Here's where we get something different, normality. For proportions, you're going to do n times p. So n is 0.23 times p. I'm sorry, that's not true. P is 0.23. N, how many students did we pick from Hewlett? 86. So let's see what we got there. 86 times 86 times 0.23. I keep doing that. 86 times 0.23 is 19.78. We have to make sure these are greater than or equal to 10, which this one is. We have to do n times 1 minus p. Let me do this the right way this time. There's 86 students that we chose from our sample, and 1 minus p is 0.77. So 0.77 times 86 is 66.22, which is also greater than or equal to 10. So the normality condition is met. Independence, we have to make sure there are at least 10 times the size of the sample. So there needs to be more than 86 times 10 is 860 Hewlett High School students. We know that that's actually true. There's over 1,000 students. We met that condition. So now we can go and run the test. So we're doing a one proportion z-test. So we go to our stat tests. We're going to go find a one prop z-test. Remember, proportions are always z-tests. So the value that we're putting in for the null is 0.23. Our x, we have 13 students who vape out of 86 from our sample. We're doing the not equal to the two-tailed test. Let's draw that. Should copy that down. Let me copy all these things down. So first of all, z is negative 1.73. P is 0.08. 0.08. And you should always draw down, maybe I didn't do it in the last one, but you should always draw what you saw here. So this is negative 1.73, and this is 1.73, okay? And what do you think we're going to do with the null hypothesis? Are we going to reject or fail to reject? Well, that p-value is bigger than our alpha of 5%. So we're going to fail to reject. So our conclusion is we should say, with a z-value of this and a p-value of this, failed to reject null hypothesis. And now we got to put context in. So why? Okay, and what is the context of the problem? There is not enough evidence to suggest that Hewlett students vape at a different proportion than the nation. Okay? That's how you do a proportion test. And this is a two-tailed test. And again, the two-tailed test, the way you're going to do it when you go to your test and we pick the one proportion z test, you're just going to pick the not equal to the thing here, as opposed to less than or greater than. That part right there is going to guarantee it's going to be two-tailed. All right, let's go take a look at the next problem. And again, what we're seeing is just some small variations in the type of problems we're doing. Okay, let's take a look at this one. At the bakery where you work, loaves of bread are supposed to weigh 1 pound. You believe that new personnel are producing loaves that are heavier than 1 pound. Now, this might be a problem because, if you're trying to save money and you just want to make sure you're using 1 pound loaves, if you're giving customers more than 1 pound loaves, then you're increasing your costs. Okay, as a supervisor of quality control, you want to test your claim at the 5% significance level. You take a random sample of 30 loaves. So again, we have a random sample here. And obtain a measure, you get a mean weight from the sample of 1.05 pounds. Now that could just be from natural variation, so it might not be more than 1 pound, but that's what the test is going to tell, right? And they're giving us a sample standard deviation. So if they're giving us a sample standard deviation, that's going to be a t-test, okay? And we want to see if they're producing loaves heavier, so it's only one-tailed, okay? And you're going to need degrees of freedom. If you're using a t-test, you should always write down your degrees of freedom. And your degrees of freedom in this case, and it's always a sample size, which is 30 minus 1, which is 29. All right, so I'm just going to state these things to move this along a little quicker. Our population is the loaves of bread that are being produced at this bakery. The parameter of interest is the true average weight of loaves of bread. They're supposed to be 1 pound, but maybe they're more than 1 pound. We want to see if they're more than 1 pound or not. Okay, let's state the null and alternative hypothesis. The null hypothesis is that, no, there's nothing wrong. These loaves weigh 1 pound, right? The alternative hypothesis is no, we're making these loaves too heavy, more than 1 pound. I'm going to check our conditions. Our conditions are, SRS. You're going to write that down. Is it say random? It does. You're going to check your normality. Well, we got 30 loaves. That's the perfect amount to make sure that you have that the central limit theorem, CLT, kicks in. So normality is met by that. And then in terms of independence, you have to make sure you're making more than 300 loaves, which seems like reasonable for a bakery to do, right? All right. So now, we already talked about what kind of test you're doing. You're doing a t-test. And we're doing a t-test because we have the sample standard deviation. When you go to your stat test, you're going to go to t-test. Let's see what we got. We got stats. Our mu value is 1 pound. Our x bar is 1.05. That's what we saw, right? 1.05 pounds. The sample standard deviation is 0.18. We have 30 loaves in our sample, and we want to see if we're making them heavier, right? Let's draw that, and let's see what it looks like. It's taking a little time. By the way, I had something graphed there. You can ignore that. All right, it looks like a pretty big section there. It's almost 7%. So this is just a one-sided test because it's just greater than. And our normal distribution looks like this, where this right here is 1.52. Our t-value is 1.52. Our p-value is 0.069. Okay? What do you think you're going to do? You think you're going to reject or fail to reject? Well, this p-value is not so small. So whenever the p-value is not less than 5%, or at least whatever they're telling you your critical value is going to be, we're not going to reject the null. We don't have evidence to suggest that that the bread weighs any different than 1 pound. From this particular sample, it just happened to be these loaves were a little bit heavier than normal. But if you actually were able to take the population, you would see that it would average out to 1 pound, or at least we don't have evidence to suggest, and that's the main thing. So our conclusion is, with t value of 1.52 and an associated p value of 0.069, we failed to reject the null hypothesis. And again, that doesn't mean anything because no context there. So what are we actually talking about? We do not have evidence that the average weight of loaves of bread is greater than 1 pound. Okay? All right, let's take a look at our last problem. Okay. Suppose a study was done to test the effect of Prozac on the well-being of depressed individuals using a standardized well-being scale. Higher scores indicate greater well-being. That is, Prozac had a positive effect. Okay, here we have 9 subjects was tested on a scale before starting Prozac and then tested after, 3 months later, okay? A box plot of the 9 scores showed some skewness but not severe. The mean difference in the subject's mood was 3.67 with a standard deviation of 3.5. Here they're giving us a sample standard deviation. Is there evidence at a 5% level that Prozac was effective? So think about what they're doing here. We don't actually have to do it ourselves in this particular problem, but they took the difference before and after. That's a paired t-test. What that means is they took 2 values from one individual and subtracted them. So it's created, you had 2 values, but you made 1 value out of it by subtracting it, and that's supposed to tell us the difference. So that's going to be a paired t-test. It's basically just a t-test. The fact is we have the sample standard deviation. They told us, now we didn't actually have to do this for ourselves. The next time I give you a lesson, I'll take a look at how you're going to look at a box plot. But here they're telling us the box plot isn't really very skewed. It showed some skewness but not severe. Remember, the t-test is robust, so we were able to still go ahead. Well, we've met basically the normality condition. So basically, the population of interest here is the subjects who have some degree of depression. The parameter of interest is how much better these people are doing after they've taken the Prozac. That's what we're measuring on this well-being scale, some sort of psychological test, right? All right, so let's state our null and alternative hypothesis. Our null hypothesis is that the mu difference is 0. Basically, we're assuming that Prozac has no effect. It's not really doing anything. The people are just as depressed before the Prozac as after the Prozac. But the alternative is that these people improved. And by improvement, we say it's greater than 0. In other words, a positive score, illustrates that the people have improved. Now, you might say, 3.67 is a positive score. They improved. But remember, there's natural variation, and if you took another sample, you might have gotten a negative 3.67. So you really need to do the hypothesis test to see if that's like an aberration or if that's really significant or not. Remember, you got to check your conditions, your normality condition. This was actually seemed to be an experiment. You would say, based on the fact that it's an experiment, the subjects weren't necessarily picked randomly, but the fact is from an experiment, we take that into consideration. Then you're going to check normality. It said that there was some skewness but not severe. So you say because the t-test is robust, as long as there's no extreme skewness or outliers, you're good to go. Independence. Now we took 9 subjects, but you could have easily taken 90 subjects to do this test. So we took 9, so independence should be okay. And now we're going to run the actual test. And again, it's just a regular t-test. Even though it's a paired t-test, the calculator doesn't care. The calculator, it's just a t-test. And we have stats, and mu is going to be 0. We always assume no difference, okay? The Prozac is not going to have any effect. X bar is 3.67. The standard deviation for the sample is 3.5. There were 9 people in the sample, and we want to see if they improve so that it's greater than 0. Let's draw that and let's see how that looks. And again, I'm doing this quickly without all the work here. And look at that. There's nothing to even really shade. You're all the way out here, 3.146, with a p-value that's 0.0068. That's a really small p-value. So what do you think you're going to do? You think you're going to reject or fail to reject? I'm sorry, reject or fail to reject. Well, with such a small p-value, we're going to reject the null hypothesis. So you say, with a t equal to 3.146 and an associated p-value of 0.0068, we reject the null hypothesis. Now again, no context there, so that's not going to get you much credit. What you now have to say is, what does this mean? It means we have strong, it's a very small p-value, so you can say we have strong evidence. You don't ever say you have proof. You just say you have strong evidence to suggest that the Prozac worked to increase well-being, psychological well-being, or whatever you might want to call it, well-being. Okay? So that's 4 examples, 4 different types of examples for you. The last 4 pages of the thing I sent you is the homework, so please work on that.